In this video, I want to talk about conditional probability. The idea of conditional probability is that we've been given some kind of partial information in our problem. The idea, we're trying to find the probability that B occurs given that we already know that A has occurred. And this is denoted by the probability of B, a bar, and then A. And so this bar is red given. This is the probability of B given A. So in order to look at these problems, we typically have our sample space S, and this time we know that an event A has occurred. So what we're going to do, we're going to replace the sample space S by A. And then we'll treat the outcomes in our new sample space A as equally likely. So let's look at an example. Two dice are rolled, and their sum is observed to be a 7. Given this information, what is the conditional probability that one of the two dice rolls was a 3? So we know that the sum was 7. So we could have had a 1, 6, a 2, 5, 3, 4, 4, 3, 5, 2, or 6, 1. Well, we can see that two of these would give me that one of the dice was a 3. Out of a total of 6 options. So 1/3. So this was the probability that we had 1, 3 given a sum of 7. In order to find this probability, the probability of B given A, we can use the probability of A intersect B over the probability of A, provided the probability of A is not equal to 0. So A determines our new sample space, which is what looks at our denominator and why our denominator is given by the probability of A. The top of this, the intersection, if we already know A has occurred, the only possible ways B could occur is if it's the same as A, if it's in the intersection with A. So let's look at some examples. Let's suppose in a certain community, 60% of families own a dog, 70% own a cat, and 50% own both. If a randomly selected family owns a dog, what is the probability it also owns a cat? So we want the probability that they own a cat, given that we already know they own a dog. Well, this will be the probability of them owning both over the probability of the thing that we know, the fact that they own a dog. Well, it says that 50% own both, so that would give me my numerator. For a dog, we know that 60% own a dog, so 0.6 on the denominator. So my probability here would be 5/6. Next, the probability that the life of a product does not exceed t time units is 1 minus e to the negative 0.1 t. Given that the product has lasted 10 time units, what is the probability it will fail in the next 5 time units? So we want the probability it'll fail in the next 5 time units, given that it has lasted 10. So when I'm looking at this fraction, the top is the probability of both of these things happening, that it fails in the next 5 and lasted 10 minutes. So we need it to last between 10 and 15 minutes over the probability that we know, the thing that we know happened, that it lasted 10 minutes. Let's start by considering this top, which is a little bit tricky. The probability that it lasts between 10 and 15 minutes. Well, let's start with 15. If I try to think through, sticking in 15 here, that means that it had failed before 15 minutes. It did not last 15 minutes. So this would be everything that failed before 10 minutes or before 15 minutes, including things that failed within 1 minute, 2 minutes, etc. I then want to remove the ones that didn't make it 10 minutes. since those are not in this group. So here, it did not make it past 15. Here, we've removed everything that didn't make it past 10. When we simplify this, we get e to the negative 1 minus e to the negative 1.5. The probability that it has lasted 10 minutes, well, that'll be 1 minus e to the minus 0.1, 10, which is 1 minus e to the negative 1. So now we need to divide these. E to the negative 1 minus e to the negative 1.5 over 1 minus e to the negative 1. And if we work this out, we get approximately 0.229. For my next example, I have this table. So we're going to let these values take on 0, 1, or 2. It tells us, the 0 tells us if there are no customers in either the self-checkout or the manned checkout. 1 tells us there's between 1 and 10 customers, and 2 tells us there are more than 10 customers. And these are the probabilities of each of the possible outcomes in an experiment that looked over a 5-minute period. I want A to be the event that the self-checkout is 0, and B to be the event that the manned checkout is 0. Now I want to know the probability of A. Well, the probability of A, this is the probability that the self-checkout is 0. So this one here. So we would find this by adding up 0.17 plus 0.02 plus 0.01, which gives me 0.2. Next, let's find the conditional probability of B given A. So this will be the probability of A intersect B over the probability of A. Well, we just found the probability of A to be 0.2. What about the intersection? Well, A says the self-checkout is 0. B says the manned checkout is 0. So their intersection would be this thing that got double shaded here, 0.17, which gives us 0.85. So the probability that the manned checkout is 0, given that the self-checkout is 0, is 0.85. Finally, let's find a PMF for the self-checkout lines. So I'm going to build my table. The possible things that could happen for a self-checkout are 0, 1, and 2. We've already found the probability that the self-checkout was 0. It's just 0.2. For the probability that it's 1, we need to look at this row and add up these values. 0.15 plus 0.225 plus 0.125 would give me 0.5. For 2, we know that a PMF has to add up to be 1, since everything in the sample space needs to add up to be 1. So we can probably figure out that this is 0.3. But we should double check by adding up this row. 0.06 plus 0.105 plus 0.135 is in fact 0.3. So this would be the PMF for self-checkout lines.